Hey, AP Statistics, welcome to the second part of 8.2. This is where we're going to actually put it all together, as it says on here. We've pretty much done the process of calculating a confidence interval for population proportion, but now we're going to actually make sure we can do the full process. And this is a process. This is what we're going to be doing a lot of these the rest of the year. When you're asked to construct a confidence interval, you actually are expected to do these 4 steps. And depending on who you ask, that you might break it up into 5 or 3 steps. There's but these are the things that essentially the AP test is going to look for that you do when you actually calculate a confidence interval. And then significance tests, I'll go ahead and warn you, have the exact same kind of process, a 4-step process. So the first thing that you need to do is state. And so state, plan, do, conclude. This is all, I'm going to be harping on this for essentially the rest of the year. We're going to state the parameter we want to estimate and the confidence level. So that's just kind of framing the problem. This actually has a little bit more to it when we get to significance testing in Chapter 9. But state the parameter you want to estimate and the confidence level. Make sure that stuff shows up somewhere. Technically, it doesn't have to be first, but that stuff has to show up somewhere. And it helps a lot if you do follow the state, plan, do, conclude, because I've graded the AP test, and when people do follow this structure, which a lot of people use the same textbook, or at least a structure, if they follow a structure, then you know where to find the things, right? I've seen other patterns, and just it helps a lot. And you're less likely to forget if you follow these steps. So first, you state the parameter you want to estimate and the confidence level. Then you identify the appropriate inference method and check conditions. This one's not going to be super interesting right now because we pretty much only have one thing we're focused on, and it's the one proportion Z interval. That's the short name for it. But we're going to learn a whole bunch more. I think by the end we cover 16 technically different inference procedures, and so you need to identify the appropriate inference method and check the conditions. That's really one of the hardest steps for people, is to remember all those conditions, and then actually calculate it. This is what some people want to do when they say calculate a confidence interval. They just do that and then they just think they're done, right? That's the math. But do is just one of the 4 steps. Perform your calculations and then conclude. So you need to actually interpret that interval and put it back into words that someone can understand. So let's go through that full 4-step process here with a problem. A recent poll of 738 randomly selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on their cell phone. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. Notice that this 170 out of 738, that's just a sample proportion. We want to estimate the actual true proportion. That's what we're going to go for with this, this confidence interval. So state, what are we going to do? We're going to do a 95% confidence interval for P, the true, and so we have to define that parameter. We're going to state what kind of confidence interval we're going to do, and you could write that out. For P, the true proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. So that is our state step. After that is plan. We need to name what type of interval we're going to do. And so this is a 1 sample Z interval for P. I call this a 1 proportion Z interval. You can kind of cram that down a little bit if you want. You could say it more broadly. It's a 1 sample Z interval for P, the population proportion P, and then go into the context. Just we've got to make sure on there somewhere we've identified that. But for now, that's the answer. Write that down and then check the conditions. We need to check the random, the 10%, and the large counts condition. In this case, the random sample checks out. They used a random sample of 738 cell phone users. The 10% condition, this one we don't know what the population size is, but what we can do is you can either check conditions or you can make the assumption. If if it's violated, the condition, we shouldn't assume it. But if they leave it up to something where we don't know, let's just assume it. Let's assume that these people are doing good statistics. Whoever's collecting this data. So we're going to assume that 738 is less than 10% of all cell phone users. That actually isn't much of an assumption. That's pretty obvious. And so you can, if you have prior knowledge, I guess you can write it as known. But it's generally good to assume it if it's not written in the problem, how big the population is in this case. So we're going to assume that is less than 10% of all cell phone users. And finally, the large counts condition. We want to check n times p and n times 1 minus p. However, we're going to be using proportions. So I showed this in the last video. You could do 738 times the p hat, which is 170 out of 738, and that just cancels and you get 170. So that actually is the number of successes. It's not the expected number of successes. It's the actual number of successes observed is at least 10. And the number of failures, if you do 738 minus that. So you can check it this way. You could also do n times 1 minus p if you prefer. 738 times 1 minus 170 over 738. Turns out you'll get 568 that way as well. So you can check that either way. But all three conditions check out, so we're ready to move on and actually do the thing. So we've done our state, we've done our plan, then we need to do, and these answers to these problems get real long, but the good news is there's fewer of them now. And so we're actually going to calculate. We're going to get our point estimate. P hat 170 out of 738 is 23%. So that's our P hat. Then we go plus and minus a margin, a z-score. Ultimately, the whole thing is a margin of error, but it is z-star is 1.96, 95% confidence interval. You could do the inverse norm of 0.025, the bottom 2.5% to figure out the 1.96. And then the margin of error, or the other part of the margin of error, is the standard error. That's our estimate of the standard deviation of the sampling distribution. So that's the square root of p hat times 1 minus p hat over n. Right? And that's all kind of fitting in that formula that was at the beginning of the first part of this video, or of the first video for this section. So that's our margin of error. There's our point estimate. Ultimately, we actually do the plus and the minus, and you get this interval. Then we're not done. So we have this interval, but what do we need to interpret that? Turn this into words, and that's what the conclude is. So we would turn those numbers into words. We could say we are 95% confident that the interval from 0.2 to 0.26 captures P, the true proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. That's what we would interpret. We don't say there's a 95% chance it's between those, right? It either is or isn't, 100% or 0%. And we don't have to interpret confidence, but we could say that if we repeated this process many, many times, 95% of the time, we know that the interval would capture the true parameter. This particular interval, I don't want to talk anything about specifics of it other than just saying I'm 95% confident that interval captures the parameter. All right, AP exam tip. If a free response question asks you to construct and interpret a confidence interval, you are expected to do the entire 4-step process. That includes clearly defining the parameter, identifying the procedure, and checking conditions. These are all things that people frequently leave out. So remember that the margin of error in a confidence interval only accounts for sampling variability. It doesn't account for bias. And so you should check that in your conditions if you have some reason to believe that the sample might be biased. What you can do in those types of problems, you actually can make a note like, I'm concerned about this condition, maybe this isn't met. That doesn't mean you just stop right there and like leave the rest of the page blank. You still probably continue the process if it's a free response question, but you should maybe point out concerns about checking conditions. But the margin of error, the way this confidence interval works, it only covers sampling variability. All right, another thing we have is choosing appropriate sample size. When planning a study, to make sure we want to choose a sample size that allows us to estimate a population proportion within a given margin of error. So if I know I want to be within 1% or 2% or 0.5%, we can do that. And we end up just having to solve our formula for the margin of error. And we can set our margin of error to a particular number. What we're going to generally solve for is the sample size. So the formula for the margin of error, and this is just the plus or minus part of our confidence interval, is z times square root of p hat times 1 minus p hat over n. All right, so to calculate the sample size, we substitute in values for what we want our margin of error to be, z star, based on our confidence level. P hat, that might be kind of weird, and we ultimately solve for n. In the end, we may not know p hat. What we might use is, we might use well, I guess we'll show this in a second, but we might use some p hat we get from a pilot study. We might just have to use some other estimate or conservative guess. So we won't know what the value of p hat is until after we conduct a study. So this means we have to guess a value for p hat in choosing when choosing n. So here are a couple of ways. You could just use a guess for p hat based on some pilot study or past experience. And so, okay, we're going to use this and then calculate the appropriate sample size based on that. If that's not okay, one thing you can do is you can go really conservative, and remember that if that p hat is 0.5, close to 0.5, that maximizes our margin of error. So we can kind of go with the worst case scenario. We go with our conservative estimate, because it's largest when that would be 0.5. And so if we plug in 0.5, and then we can end up solving for that sample size that would ensure that our margin of error will be within a range. So ultimately, it kind of can summarize that up into this table. So we're trying to determine a sample size. We're trying to solve for this n down here. We can, so we're trying to determine a sample size n that will yield a confidence interval for a population proportion with a maximum margin of error of ME. Solve this following inequality. So you want to be 1% with 95% confidence, that's going to be a 1.96. If you want it to be within 3% with 99% confidence, right, that's going to be, I think it's 2.645. You can figure out the z-star for that. If you want to be 90% confident, you can change that and you can choose what you want that margin of error to be in that confidence level. Have a p-hat or go with a p-hat of 0.5 as the conservative approach, and then solve for n. And so make sure that you do that properly. You solve your algebra. So example problem, a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that he will be required to pay for. One value of interest is the proportion, P, of customers who are satisfied with the company's customer service. She decides that she wants to estimate to be within 3 percentage points. So that's our margin of error at a 95% confidence level. How large of a sample is needed? That's all we need to actually do this calculation. What we're going to do is we're 95% confidence. That means our z-star is going to be 1.96. Margin of error is 3%. So 95, 1.96, 3%. And then we don't know what the population proportion is. So if we go worst case scenario that it's 50%, we'll plug that in there. 0.5 for p-hat and 1 minus 0.5. That actually maximizes this number. So I know that if I get an n that's big enough, I know I'll at least be good. And it might be a little bit smaller than the 3%. So then to solve this, you divide by 1.96, and just I'm taking you through the algebra here, make sure that you got this. Then we square both sides. And then at this point, you can like cross multiply or multiply by n to get to the other side, whatever you want to think of that. And then divide by this 0.03 over 1.96 squared. And be really careful to keep a lot of decimals in your calculator. That number is really tiny. And it needs to be pretty precise to get this solve for n accurately. And so you end up having here you've solved for n and you would type all that in. So you might want to wait till the very end to type all that in. But you should be careful. Use like second answer in your calculator, because when you square this tiny fraction, it gets really, really tiny. You want to be accurate with that. And so that ends up being there. N needs to be 1067.111 repeating. However, it might not make sense for a sample size like that. So this is one of those cases where we do want to go up to the next whole number. And so we would need to get a sample size of at least 1068. We don't just round down. We need to make sure that to be certain, we always want to go above that number so that our margin of error is definitely small enough.